Here we're going to explore giant ionic compounds and how their structure impacts their properties. In a giant ionic compound, the oppositely charged ions are arranged in structure often known as a giant ionic lattice. This structure is regular and results in the formation of a crystal. In the diagram, you can see sodium chloride, the smaller positively charged sodium ions bonded to the larger negatively charged chloride ions in all directions. This diagram only shows one layer of the structure, but it will continue out in all directions to create a 3D structure. Between the ions, there are very strong electrostatic forces, a term which describes the attraction or repulsion between two charged particles. Since the ions have opposite charges, they will attract each other. Due to the strength of these bonds, they require a lot of energy to break them and separate the ions, meaning giant ionic structures have high melting and boiling points. Since these strong bonds mean the ions are held firmly in place, ionic compounds do not conduct electricity. However, when molten or dissolved in a liquid, the ions are free to move and carry a charge, so the ionic compound will conduct electricity in these states. Here we can see an expanded diagram of an ionic lattice. This shows the crystal lattice of sodium chloride. It can be drawn by starting with one ion and adding the other type in all directions. By continuing this pattern, you'll get the 3D diagram shown here. Just remember, ions should not be bonded to another ion that is the same type as itself. Some ionic compounds have stronger electrostatic bonds than others, resulting in higher melting and boiling points. The general pattern here is that the larger the charge on the ions, the stronger the bonds, and the higher the melting and boiling points. For example, in sodium chloride, the ions are 1 plus and 1 minus, with sodium chloride having a melting point of 801 degrees Celsius. Magnesium oxide with 2 plus and 2 minus ions has a melting point of 2,852 degrees Celsius.